Thank you all for joining our press control webinar. This is going to be the first in a series of webinars hosted by Delta. So at the end, we'd love to hear your feedback, see if there's any other topics that you would like to hear covered. Some ideas would be a general controls webinar, testing application webinar, but would be very interested to hear ideas from you as well. So let me jump into our presentation. A brief introduction to Delta Computer Systems in general. We are a manufacturer of high precision motion controllers. That's our main, our core offering. We focus very specifically on high quality products. Make sure that we deliver something with great hardware, a controller with great hardware. Our software, RMCTools, which you'll get to see here in a little bit. We've spent a great deal of time and effort to make this a user-friendly program, something that makes very complex tasks as easy as they can be. And I hope you'll get to see that here today. We are very much so dedicated to service and support, whether that be our distributors, our sales team, our support team. We really all want to make sure that if you have a Delta product, that you are up and running as quickly as you can be, and that you have the resources that you need. Now, I know with this webinar, there's going to be a range of experiences here. So we're going to be covering the fundamentals of using RMCTools, setting up an axis, getting things running. And we're going to slowly build onto that until we get to the second part of this webinar, where we will start to dive into a little bit more detail-oriented applications. So there are many press applications that we have been part of. Here's a list of a few. You can see that we've done a lot in the press industry. Powdered material presses, whether it be ceramic or metal. Press cushioning, perhaps something like a 4-cylinder press that needs to be leveled by the cushioning. Bearing presses, forming presses, multi-cylinder leveling, synchronization. Again, this could cover kind of a range, but we'll get into this idea further on in the class, but having 4 cylinders and maintaining a level at all times. Single cylinder presses, forging presses, draw presses, press rolls, hot presses, brake presses, die cast, and many more. Our 40 years of experience covers a wide audience, a wide range of applications. And yeah, there's a lot that we've done, and in addition to all this, we've got great notes, great application papers for all of these topics. And so if one of these has piqued your interest, again, please use that question box, reach out to us, and we'd be happy to give you some more information. Okay, so what is the benefit of using an RMC or one of Delta's motion controllers? Well, you would expect great position and velocity control. And if you've used a Delta RMC controller in the past, you would see this. This is something that is kind of a given for us. We focus, heavily on providing great control in general, but many users have used us for position and velocity control. Some things that you may or may not be familiar with are that we actually are very good at doing a smooth transition from a rapid advance to a press mode. So we're able to control that rapid advance, moving quickly up until right before you're making contact with your part, right? Bringing those production times down, bringing your cycle time down, and getting you as much throughput as you can. We also do a really good job with a quick, seamless transition from position velocity control to force control. This is another thing that's very tricky. It's something that Delta does really, really well. And you'll be able to see that here, both in a physical system and in a simulated system. but it's a tricky transition to do. It's just something it's very tough, but we've got a lot of really great tools to make it easy for you and to make that transition smooth and seamless. Simultaneous sequencing. This is another thing that we here at Delta have spent a lot of time perfecting and trying to give you the best experience possible. We've spent a great deal of time with our user programming. You'll get to see that again here as we go through, but just really trying to give you all the tools that you need to be able to accomplish any logic sequence. Synchronized position control while controlling total force. This is kind of a secret sauce type application that we have here at Delta, and something, again, that we've put a lot of thought and a lot of effort into, and we're going to cover this in great detail in the second part of this course. I'm going to go through how we do this, some of the thought process behind it, and then how you get from the theory into putting it into one of our motion controllers. So we'll be talking about a few different physical setups as we go through this course. And I want to give you a visual representation of what this is going to look like. So our most basic axis is going to be a position control axis. The wiring here is going to be fairly simple. We'll have a control output to our valve and a position feedback coming from our transducer here. So when this hydraulic cylinder moves back and forth, this position feedback, this transducer, this electronic measuring tape is going to be sending us the position that we're at, and it's going to be sending this. We're going to call it a loop time. For us, it's generally every millisecond. So every millisecond, every 1,000 times a second, you're going to get feedback from the position, and you're going to be sending an output to the valve. Another axis we could have is a position force control axis with dual input. This is actually how we're going to be controlling force. This is what our lab setup looks like, and this is how I'm going to be simulating it today. But in this application, you still have the same control output, you still have the same position feedback, but you're going to have two pressure transducers, one on either end of this cylinder here, and based upon the differential pressure and the geometry of your cylinder, we're able to determine what the force is, what force that cylinder is seeing. So we're able to control force in that way. The second way that we can control force is with a load cell. Here's a good example of it. We've got the load cell mounted on the end of the cylinder here, and you've got force feedback coming into your controller there. Again, guys, as I'm going through this presentation, I know that I'm going to be covering things fairly quickly. So again, just really encourage, if you have any questions, please use that question box. Really want to make sure that you're getting the most out of this, that your questions are answered. Use that question box, send us an email, give us a call. We'd be more than happy to talk with you. Okay, here's a few recommendations from Delta as far as the physical setup goes. To have precise position and force control, we highly recommend zero overlap or slightly underlapped servo proportional valves. Having a valve like this is going to give us the best chance for success. If we have a nice valve like this, you're able to get very, very good control, and you're able to do it fairly quickly. If you don't have a valve that's quite fit for the application, Delta does have different ways that we can try to get around it. But if at all possible, we highly recommend that you try to go with a zero overlap or slightly underlap servo proportional valve. Prefills and cartridge valves will most likely be used in the rapid advance. That's just part of the press industry, really. When you're using these, use solenoid operated or with an external pilot to ensure they're in the desired state. And this is really going to make it easy for you to do the setup, get your tuning done quickly. It's going to make things a lot more simple when it comes time to try to tune things up or use the PID to get fine control. This is going to, again, just save you time, give you a much easier time with the setup. Fast, accurate force position feedback. This is something that we definitely need to have good control. As far as position goes, we love using SSI feedback. It works great, high precision, low noise, and if for some reason, perhaps you're in a situation where things maybe for one reason or another, maybe cylinders are undersized and you're having problems with oscillation. If we have this high quality feedback, we're able to use what we call the second derivative gain. If you'd like to know more about this, again, please use that question box. We can talk more. But using this gain, we're able to compensate for systems that aren't optimally designed. And this is, again, something that's very unique to Delta, something that we've had great success with. I know I personally have had great success tuning up presses that otherwise were uncontrollable. But using this second set of gains and the high quality feedback, we were able to get a really nice smooth transition and save the day. Load holding valves should be solenoid operated or held open with an external pilot source. Again, this is going to make your setup much easier. It's going to just help things. It's going to reduce the time that you need, and it's going to make it so much easier when you're trying to do your commissioning, when you're trying to set things up. So just a brief view on the physical setup. We have another resource, our hydraulic design guide. If you'd like a hydraulic design guide, just to read it over, there's a lot of good information on presses. There's good information on just general applications. Again, please reach out to us. We'd be more than happy to send you over a copy. Okay. So we're going to be going quickly through this, but like I said, there's more information available. Ask questions. We've got some great online resources at deltamotion.com. If you have RMCTools downloaded, our help topics are, we put a lot of effort into our help topics to try to make them clear and precise and give you all the information you need. But what I'm going to go through now is how do we actually set up an axis? How do we get something running if we had, say, a single cylinder? Okay, so what we're going to need to do first is define our inputs and our outputs. We're going to, excuse me. We're going to be defining our inputs and outputs. Where are our inputs coming from? Are they SSI? Are they analog inputs? We're going to be defining that there. And then also, where are outputs going to? Which card are they coming from? And then where are they going to? Are they going to a valve? Are they going to something else, maybe a motor? Where are these outputs being sent to? Next, we're going to show how to scale our feedback. I'm going to show you guys how to briefly do the setup. I won't go through all of it, but I want to show you that there's some really nice wizards to get things set up. Again, just save you time, reduce the amount of effort that you're spending on trying to set these up, and ultimately get you up and running faster. And then we're going to, finally, we're going to be testing our axis here, make sure that we actually do have control over the system, that things are moving, and from there we'll go on to our next step. So what I'm going to do here is I'm going to open up RMCTools. This is our software. Right now I'm using an RMC 200. This is our latest and greatest product, up to 32 axes of control, but this software is the same software that's going to be used with an RMC 75 and an RMC 150. Each of those controllers are great controllers. They all work very well. Really, it comes down to how many axes you have in your system. Okay. So what I want to show you is how an axis is set up. I'm going to go over here to Access Definitions. And you can see that I have a few axes already set up. If I didn't have one of these axes, I'd click this new button here. Since we already have these axes here, I'm just going to click Change. But this is going to be the same window here. Okay. So you can see our setup. Right now, we've got a output coming from our CV8 card. Our first feedback is coming from an S8, and our secondary feedback is coming from an A8. These are just all cards on the RMC itself. I can change which outputs I'm connected to. And everything is very simple, very easy to set up just like that. You can also see we've got a really nice display on where is the CV8's physical wiring, where is the S8's physical wiring, and the A8. So really, really nice. If you're trying to go through and you're trying to troubleshoot, we've got all that information right there. Okay. So this is set up. It's ready to go. What I would normally do next is look at my position offset scale and my force offset scale. I'm going to launch our wizard here. If you know the resolution of your transducer or encoder, you can click next. We have a linear transducer, so I'll click next. And my transducer, maybe it's a 1 micrometer transducer. That all looks good. So I'm going to click next here, and here would be my new value. I'm going to cancel out of this, but just again wanted to show you guys a brief view of how to set up this axis here. Okay, so it's set up. Right now I've got an actuator view. This is showing me where all my axes physically are. I'm going to go ahead and move axis 1 here. So I'm going to put a direct output. I'm going to open up my valve a little bit for axis 1. So I'm going to put out 5%. And I can see here that my axis number 1 is it's moving, right? Axis 1 is moving up. That's what I'd expect. If I send a negative voltage here, and I'm going to quickly make sure these others are set up here to not move, just so that nothing's confusing. Okay, let's send a -5 to our axis number 1, and we see it retract. So what this would tell me is that things are all set up correctly. We're ready to go on to our next step. Okay, so our axis has all been defined. We're ready to go. So what we would do now, and I've already got this tuned up here, I'm going to give you a brief introduction to our PID gains, how they work, and what we need to do to get things accomplished here. So the gains that we're going to be working with and that I have set up right now are the proportional gain, the integral gain, derivative gain, and that makes up your PID, and then velocity feed forward and acceleration feed forward. The second derivative is that special gain that we only throw in if it's needed, but it's great to have if it's there. It basically accounts for springiness in a system. With some systems, it's for one reason or another, they weren't quite designed optimally. For other systems, it's just how it is. There's no getting around it, and that's the way it has to be, and that's okay because we can work around it. Okay. So our proportional gain here. Our proportional gain is going to be looking at the error proportional to the position error. So it's going to be looking at the difference between our target position, this light blue line here, and our actual position, this red line here. So it's looking at this instantaneous error. right? It's looking at one point in time and it's seeing what the difference is. And based upon that, it's going to be sending output to our control output. And this green line here is our control output. So this is what is actually going to the valve. So based upon this error, the output to the valve is changing. The integral gain works similarly, except instead of looking at the instantaneous change between or error between the actual and the target position, it's going to be integrating the error here. So it's going to be looking at the area between the two. And over time, this integral gain is going to build up, and over time it will wind down. So again, this is getting fed to our control output. This is going to the valve on our controller, or on our system rather. Our differential gain is a little bit different. It's going to be looking at the error due to velocity, or the error proportional to velocity. So this pink line here is our velocity target, and this blue line here is our actual velocity. So based upon the error between these two, the differential gain is going to be sending, again, feedback to the controller, which then adjusts the control output, the output that's going to our valve. Okay. The feed forwards work a little bit differently. Rather than like the PID, where there's a scale of answers that could work with your system, the feed forwards generally have one correct setting if you have a linear system. And again, that kind of goes back to our recommendation for the valve. We recommend having that zero overlap or slightly underlap linear valve. The velocity feed forward is basically telling the controller what kind of ratio you have. So I'm going to give you a for instance. If I sent 1 volt to my controller, if I opened up my valve, moved that spool over 10%, maybe I get a velocity of 2 inches per second. Well, if my system's linear, I can say, okay, so I moved 10%, I got 2 inches per second. Therefore, if I moved 20%, I'd expect 4 inches per second. If I moved to, or if I sent a signal of 50%, I would expect to move 10 inches per second. So basically what we're doing is we're telling the controller, this is the final voltage that you need to eventually ramp to. This is what the ratio looks like, and so therefore it's giving the controller some idea of where it needs to go rather than just having the controller react to changes. The acceleration feed forward works similarly, but instead of helping us with this constant velocity portion, you can see here this pink line, constant velocity, and you can see that it becomes a straight line here in the position. But the acceleration feed forward isn't going to help in this area that the velocity feed forward was helping us in. Instead, it's going to help us out at the beginning of our moves and at the end of our moves. It's going to give us an extra boost of voltage, and you can kind of see it here. You can see it here on this green line as well, where that extra boost is coming in, and it's helping us accelerate up to where we need to be and decelerate down to where we need to be so that we don't overshoot. All these gains together provide a really nice, very adaptive control that is going to keep systems in place. With most every system, these are totally fine. Sometimes you need a little bit extra though. Sometimes you need that second derivative gain. And again, if you'd like to know a little bit more, please reach out. We'd be happy to answer any questions on that. Okay, so what I'm going to do here before I get into showing you guys how to set up force control, I'm going to jump back to RMCTools, and I want to show you what position control looks like. I've already got my axis tuned up. I'm going to be moving it around a little bit here. I'm going to show you guys a user program as well. I'm going to say, let's say we've got a sequence of events that we want to try to go through. Let's look at what that looks like in RMCTools, and then I'm going to show you what it looks like on a physical system. Okay, so let's jump right into it. In my project view here, I'm going to go down to plots. This is a great tool that we have. You can see I have a plot saved here from before. I'm going to be wanting to use my axis 1 here. And I'm going to go ahead, I'm going to give this a move command. So I'm going to type in move absolute. This is our basic move. We'll try something like this. Move to a position of 8 at a speed of 7, an acceleration of 35, and a deceleration of 35. So I'm going to send this here. And you can see that my axis has moved. I can see the simulator has shown me that my actuator view has changed. And I can see exactly what we were talking about earlier, right? I can see these gains here. I can see that things are actually tracking really well as well. You probably can't see it so well here, so let me turn off the actual position, the red line here, and you'll see that my target was right underneath the actual position. So all of this to say, this system has already been tuned up fairly well. I can look at my tuning tab here and you can see my gains. I've got a proportional gain of 150, integral gain is around 700, but you can see that things have already been set up here. Okay, so that was our move. What I want to do now is maybe I've got a sequence of events I would like to have this axis move in. So I'm going to open up my user program that I created, single axis position, and we can see what's actually going on here, right? We can see maybe we had a sequence of events we were trying to follow. Perhaps the first in the sequence was we wanted to move to a position of 3. Okay, so we've got our move absolute. We're moving to a position of 3. We're going at a speed of 3, an acceleration of 15, and a deceleration of 15. All right, so we're doing this move command here. Next, we're going to be waiting to see when we're in position. So I'm sending this to axis 1, and then I'm waiting until axis 1 is in position. Once this is in position, perhaps I want to wait for a couple seconds before I go on to my next step, right? Maybe you don't want to execute any command, you just want to wait. Well, I can put in just a link type. I can say I'd like to delay for 2 seconds, and after that, I want to jump down to my next step. Okay, after this, perhaps I am going to be moving to a position of 6, again, with the same speed of 3, accel 15, decel 15. Again, this is going to axis 1, and we wait until we get to that position of 6. Okay, next, maybe we go to a position of 4. We're setting ourselves up for something. We're trying to go to the beginning of a sine wave command. So maybe that sine wave starts at a position of 4. So we use this command to get to the beginning there. Once we get there, we're going to send this sine start command. I want to move in a sine wave pattern, and this is just going to be free floating. We're not quite going into press mode yet. I'm going to show you guys that here in a second, but for right now, we're just free floating. In the air, we're going to be doing a sine wave. Our sine wave is going to have an offset of 4, an amplitude of ½ an inch, a frequency of ½ a hertz, and 6 cycles. So I'm going to do 6 sine wave cycles. Once all of my cycles are complete, I'm then going to go back to a position of 2 and get ready for my my next sequence, right? This could be, you know, possibly this is with the press, possibly this is for another application, but this is a quick sequence, and it's, you know, there's a lot that's happening in this program, but as you can see, it's laid out where it's pretty easy to understand what's going on, and more than that, it's very easy to program. Something like this, you know, it maybe take you 10-15 minutes. And that would be if you had to, you know, really get familiar with stuff. We've got a lot of tools for entering things in like this that make it much easier than you don't have to type things in. We've got a really nice setup wizard, very, very user-friendly programming. Okay, so now I want to demonstrate this for you guys. I'm going to start training my plot here. I'm going to right-click on this user program, and I'm going to click Run Program. Okay, so now we're running. We're going to that beginning of our sequence there. We go up here. Now we're doing our sine wave. So far, so good. This sequence is looking just like it should be. After 6 cycles, we're then going to go back to a position of 2. And that was our cycle, right? If I run this again, it's going to run that same cycle over. We go up to 3, we wait for a time, go up to 5, down to 4, do our sine wave again. These could be your cycles here. And it didn't take long to, or it wouldn't take long to program this up, rather. So there we go, we've got it. It's one thing to show this on a simulator, it's another thing to show an actual system doing this. So what I'm going to do is show you this on a system that we have here at Delta, our 2-cylinder press. So let me open that up for you guys. Okay, 1 second here. All right. Now this is going to be the exact same sequence that we saw just before. You can see our cylinder here, axis number 1 on the right. We're now doing our sine wave. Things are working just like we'd expect. You can see, I'm going to show you the plot from this here in a second, but it's very fine control. Here's the beginning of that move, just showing you it again. We went down to a position up to 4, and now we're doing our sine wave. Very, very precise, very accurate. I'm going to show you a plot of this actual system so that we can see it, and we can actually see what this is doing here. Okay. Let me share my screen with you again. And open up RMCTools. Okay. So this is the plot that I took from that physical system. You can see that my target position is right on top of my actual position. It's tracking very, very, very well. There is a slight difference, right? You can see that we're a thousandth of an inch off here, but generally, it you know, with a good system like that, it is controlling really, really well. So things look good on that front. Okay, now let's say we're happy with our position control. Maybe this is a press application. Maybe it's just a single axis press application where we now want to go ahead and start doing some force control. Well, if we wanted to go into our force control, what we do, so I'm going to jump back into my PowerPoint here. Normally what we do is we tune our force loop up as well. Right now I already have this tuned up here, but you can see that the same gains are active: a proportional gain, an integral gain, a derivative gain, feed forwards. Each of these gains need to be tuned as well. So once this is all set up and tuned here, what I'm going to be trying to achieve is something like this. You guys are probably familiar with a plot like this. Perhaps this is a press cycle, right? The first part, maybe your platen is floating in the air. You want a rapid advance. You want to move very quickly. Again, this red line is our actual position. We can't really see our target position because we're tracking very well. Black here is our actual force, and yellow here is our target force. So first part of our cycle, we've got a rapid advance. We want to quickly accelerate, quickly move with high velocity right before we make contact with that physical part. We don't want to slam into the part. We want to go really quickly right above it, slow down. And so here's our pre-press mode. We're slowing down right before we make contact with that material. You can see that this black line hasn't quite gone up yet. It's just slowing down, but it hasn't really made contact. Then as we're slowing down, once we see a little bit of force, we're going to go into our pressing mode. We're going to go into force control here. So reason we do this is because you don't want to try to go into force control too early. If you go into force control before you're actually contacting the part, what's going to happen is the controller is going to send a little bit more control output. and it's going to expect a change in force. We don't see that change in force, so it's going to continue to send more and more and more output. Doing something like this, what it's going to end up happening is the cylinder is just going to slam into the part below it because it's going to keep building up because it's not seeing any feedback. So this is why we really want to wait to go into force control until we've actually made contact with the part, because then we're getting real feedback, we're getting good feedback, and we're not going to damage anything. So we're in pressing mode here. We quickly accelerate up to our target tonnage. For us, this is just going to be 1,000 pounds because we're using that little system there. So we're going up to our target force, 1,000 pounds. Once we reach that, we're going to delay for a time. Maybe this is just part of your press cycle. And again, this is just to show you how we would do things as far as Delta is concerned. So we're delaying for a time, and then perhaps we've got a slow force intensification period, right? Maybe we're slowly moving up to a greater force. For us, this is 1,500 pounds. So we slowly move up until we get to a greater force. We then again delay for a time, and then we'll say this is the end of our press cycle. At this point, we're going to retract. We're going to ramp back down to a force of 0. We're still in force control, so we've got total control over how we want to disengage from that part. So we're disengaging here. We get to a force of 0. We know we're kind of, just right, barely touching that part. And so then we start our rapid retract. We retract back here, and we're able to lift that cylinder back up, lift that platen back up, and we're ready for another cycle. So this is our goal, right? This is what we're trying to achieve. Now, what I'm going to do is show you both a video of how this is going to look, and also how would we do something like this in our Delta programming? What would something like this look like? So I'm going to jump to RMCTools here. Okay. What I'm going to look at is my single axis force program here. Okay. My first step, I could see that I'm moving to a position of 10. With this system, I'm going to encounter force at 9.5 inches. So I'm trying to move to a place where I know I'm going to encounter force. I'm never going to get there though, and I'll show you why in a sec. We're going to go at a speed of 2. For this system, that's a fast speed. Different systems, fast is kind of relative, but for this system, 2 inches per second is fairly quick. We're going to be going at a acceleration of 10 inches per second, a deceleration of 10 inches per second, and we're going to wait until we've got to a position of 9. So we're going to wait until we're fairly close to our part, right? We know we're going to make contact at 9.5. Okay, once we get there, we're going to send another command, another move absolute, again to a position of 10, but you can see our speed has been reduced by a factor of 10, right? This is because we're really close to that part. We need to slow down now. So we're slowing down. Again, this is all going to axis 1. Once I see my axis 1 actual force go greater than 500 pounds, I know that I've made contact. There's no doubt, right? This 100%, we know we've made contact with the part. So we're ready to go on to our next step, which is an enter pressure force control with a time. So we see we've made it to 500 pounds. Next, we're going to ramp up to 1,000 pounds. Maybe this is my pressing my pressing force, my pressing tonnage that I want to ramp up to. I'm going to ramp with a linear ramp. You can choose if you want an S-curve or if you want it to be linear. I want this to take half a second to ramp up to where you need to be. Again, you can see how configurable and how easy these programs are to use. Very, very nice. Everything's adjustable. It's going to be good for your application. Okay. Once we are at force, once axis 1 is at force at this 1,000 pounds, we know that we're ready to go on to our next step. Maybe from our application though, we want to immediately go ahead and start a sine wave. Something like this could work, but what I'd actually like to show you guys from this point on is a little bit closer to what the plot I showed you there earlier. So I'm going to jump to this program here at same beginning here, but after 1,000 pounds, I want to delay for 3 seconds, exactly like we were doing earlier there, as I showed you in that plot. Then maybe we have our slow intensification, right? We're going to ramp up to 1,500 pounds, and we want that ramp to take 5 seconds to get up to that intensified force. Okay, again, this is being sent to axis 1. We wait until we get to this 1,500 pounds. Then we're going to wait another 2 seconds. After that time period is done, we're going to ramp back down to 0 pounds. So this is when we're relieving pressure, right? We're relieving force. We're starting to retract our cylinder here. Once we get to this force of 0, we're then going to do a quick move. And this is a really neat command that we have here at Delta. You could use this for the drop down as well. But what you're able to do here is kind of a combination between open loop and closed loop. The beginning of this move is going to be open loop. I tell it, I want you to ramp to 80%. You could even say 100%, but just, go as fast as you possibly can. But when you get close to this final position of 3, I want that closed loop, that PID, to take control, and I want a really nice smooth stop as I'm coming back up, and I want to hit that position of 3. So it's kind of the best of both worlds. It's a really nice command to use. All right. So we've gone through this command. Again, guys, I know that this is a lot of information very quick. For some of you, this may be review. If this is totally new to you and you want to dig deeper, again, I recommend reach out to us. We'd love to speak with you one-on-one and make sure that you have what you need to be successful. Okay, I'm going to jump back to my plot, and I want to show you guys this program running. Okay, let's run this program here. So I'm quickly moving up to where I need to be. You can see I slow down. I make it to force. I'm going to analyze this plot here in a second. Now we've got our slow intensification. We've made it there. We're going to drop our force back down to 0. And then our position is going to take control here. So let's look at this plot and verify a few things that you guys are going to care about. Okay, so this quick move right here, right? I'm able to very quickly accelerate up here. I can see that I've got a velocity of around 8 inches per second for this system. That's very quick. This period here, this is our quick move, right? We're quickly moving up to where we need to be. Then this period right here, this is where we're slowly approaching our part. Now, if I zoom in a little bit more, I can see my black line here. It's starting to rise up, right? We're starting to see a little bit of force. So we've most likely made contact somewhere around here. But we continue to go up until we know for sure that we've made contact. So right here, I can see that my actual force is just under 500 pounds, and I can zoom in even more. As soon as I cross 500 pounds right here, you can see my yellow line. It spikes up, right? Spikes right up immediately, and what that tells me is now I'm in force control. So from this point on, we're trying to control force. I can see that I'm ramping up to my final target. Perhaps this needed a little tuning, but it's not overshooting by too much here. My target force is 1,000 pounds. I overshot by about 10 pounds. If we spent a little bit more time tuning this system, you'd get even better results. This one was just tuned up fairly quickly, but you can see, right, there is a little bit of overshoot, and that's fairly common. But the nice thing is with the Delta control system, we're able to tune for specific things like this. If, say, you absolutely do not want this to overshoot at all, that's just paramount. That's the one thing we can't do. Well, we can tune, we can program specifically for that and make sure that you're not going to go over your target force there. Okay, So now we're holding this force, right? Our black line here, our force is being held very well. You can see that this S curve here, it's a bit more smooth. Again, it helps with this overshoot, right? We did the linear transition right here. This linear transition, good for some things, but again, like we were saying, you can program things to make it a little more smooth. This S curve, you can see we're transitioning a little bit slower, and there's really almost no overshoot at all to speak of. It looks like 0.2 pounds here is what we overshot with this S curve. So very nice. We slowly intensify up to 1,500 pounds. You can see right here. Wait there for 2 seconds. That's this time from here to there. And then you can see this time from here to there, we retract, right? We're no longer we're trying to disengage from that part that we're pressing on. So I can see that my force, my black line here, it's ramping down to 0. And then right here, where this yellow line flatlines, that tells me, okay, I've transitioned into position control again, right? I've handed that off to position control. We've disengaged from the part. So now we're going to do our quick move again, and we're going to be jumping down to a position of 3. So we've done our entire cycle. All right, what I'm going to do now is play a video. We're going to see that same press that we were looking at earlier. And I'll show you this single cylinder force control. Okay, so we're in position control, going quickly. We slow down. You see how much that slowed down there. We press to our 1,000 pounds. It's a little bit difficult to see it here. You can kind of see those rubber plates at the bottom are flexing a bit, but we slowly intensify up to 1,500 pounds. Go to 0 pounds, and now we retract quickly up to where we need to be. Show you guys that one more time. Position control here, slow down, go into force. We've made it into force. We're controlling now. We can do whatever we need to do. And then we've got our disengagement from our force here. And back up to the top. Okay, let me show my screen again. Okay, so that was our physical system, right? And again, it's the same program. You can see that there's quite a few different options that we've got for force control. There's even a few more. We've got a force limit control as well, so you can be in position control. But rather than ever going into force, you can say, I'd like to go to a specific position, but I never want to cross a specific force. We can limit the force. And again, it's just like it sounds, it's limiting that force. And that's another control algorithm that's available as well. If you guys are interested in that, again, reach out. We'll give you some more information on it. Okay, let me jump back to my slideshow. So you can see we're able to achieve our press control here. Now, let's say we introduce another cylinder into this. Maybe it's not just a single cylinder press and you have 2 cylinders or 4 cylinders or more. Well, it's going to be very similar to what we saw before. We're going to start with our setup and tuning of our second cylinder. We're then going to synchronize our position, and we're going to gear this cylinder to a master. I'm going to talk about this here in a little bit, but what this is going to do is it's basically like a physical gear, right? If you can imagine 2 gears interlocking, when one moves, it causes the other to move. That's what we're going to be doing with our physical axes here. So when one axis moves, the other one's going to have to move in unison with it. And that's going to give us our synchronized control. To do this, we're going to have to program our logic. So what I'm going to do is I will show you what this logic is going to look like. A good example for something that's synchronized is this project that we were working on here, 4-cylinder vehicle roof structural test press. So we needed to make sure that each of these 4 cylinders, they were all level with each other at all times. Okay. And there's 2 options for this. I'm going to show you guys different leveling options as well. But for this purpose, we're going to be gearing to the physical axis. Okay. So let me open this up here, open up my user program. And this is what it's going to look like. I'm going to assume that my second cylinder has already been set up. It's already been tuned. That's cylinder 0. But what we're going to be doing for this is synchronized position control. So right now, we've got a command that's getting sent to both axis 0 and axis 1. Okay, this command is being sent to both these axes. We're going to be sending a command to go to a position of 2, a speed of 1.5, an acceleration of 10, and a deceleration of 10. Then we're going to be waiting until both of these axes have hit that final position, right? We want to make sure that these axes are level and that they're ready for our next step. What we're going to do after this is we're going to send a gear absolute command. So we're going to be gearing these 2 axes together. I'm going to be, for this, for the purpose of this example, I'm going to be gearing to the target position of axis 1. Again, the target position is that blue line that we've been seeing, right? The objective here is we want both of our axes, both cylinder 0 and cylinder 1, we want them to have the same target. We want them to have the same goal, right? You want them to be lined up and following the same master. So we're choosing axis 1 for that master. Now we set up a ratio. What does this relationship look like? Well, I want this to be a linear 1-to-1 relationship. So I'm going to say when the master, that's axis 1 target position, is at a position of 0 inches, I want the slave to be at a position of 0 inches. When the master is at a position of 9 inches, I want the slave to be at a position of 9 inches. That's going to give us that nice linear relationship. Okay. What this bit tells me here, this target generated superimposed busy bit, what this tells me is just that everything is geared together and we're ready to go on to our next step. Again, we've got really, really nice help topics. So if I were to click here and press F1, popped up on the other screen there so you guys couldn't see, but we've got really nice help topics for each of our commands. You can see, you know, what target generator, superimposed busy bit, what does this do? We can look at what the faults do. We can look at, you know, how are things working here, but we've got really great help topics for each of these commands. If you have any question in your mind, what is this actually doing? I want to make sure that this is the command I'm looking for. Okay, so past this, we are geared, right? Axis 0 is geared to axis 1. So I can move axis 1 here. I'm going to move it to a position of 3, and axis 0 is going to follow that axis 1. I'm going to do just the same sequence that we've seen before, right? The same one that we saw before with the single cylinder where we're moving in free space. We do a few moves. You can see we move to 6, we move to 4. We start our sine wave just like we saw before. We do our 6 cycles here. Wait until we get into position, and then we retract back to the top, right? So we've seen this sequence before. The only difference here is now we want this to be a synchronized sequence. Okay, so let's see what that actually looks like. Okay, on this plot, I've got axis 0's target position is light blue, axis 0's actual is red, axis 1 target is gray, and its actual is orange. So I would expect all of these to look down, all of these to be synchronized together, right? They should all be right on top of each other. Okay. Let me run this program here. See what happens. Okay, so things synchronized together. We're moving in unison. You can see everything is right on top of each other. This looks exactly like we'd expect, right? Everything is synchronized. And I actually have another bit here as well, actual skew. This is measuring the difference between the two axes, so I can see how well are these actually synchronized. So if I look at the first part of this plot here, I can see that my axis 0 is at a position of 0. And you can kind of see it on the side here with the legend as well. But you can see that axis 0 is at 0 and axis 1 is at 3. When I issue this command, they come together, right? Axis 1 is getting there first and axis 0 gets there last, but they wait until both have made it there. So what I'm going to do here, I'm going to look and see what my actual skew looks like. So I can see right now I've got 3 inches of skew, right? They're 3 inches off from one another. But as they come together, as soon as they're both here, right now there's a thousandth of an inch between them. We're tracking really well, right? We track very, very well. And now we're only sending commands to axis 1, but you can see that they're both linked together. They're following our sequence. And you can see that there's little tiny bits of difference here. It's just a thousandth of an inch, but it isn't just you know, totally out there. It is showing you that there is some difference between the two. Okay, and like always, it's one thing to show you this in the simulator. It's another thing to show you a real video of this happening. So let me open up our video here. Of our position control, and I'm going to show you what this looks like on our press. Okay, so you can see they're not level, they become level, and now they're synchronized together. They move to a position, move to another position, begin doing their sine wave, and you can see that these are they're both synchronized together. They're totally level, and I'm going to show you a plot of what they look like here in just a minute. Okay, see it one more time. You can see that they level, come down to a position, head down again, and then go into their sine wave move. And you can see that these are synchronized really, really well. That platen is very level there. Okay. Let me share my screen again. Okay. Now, what I'm going to do here, I want to show you a plot of what this looks like here. So this is the plot of the physical cylinder that we just saw. You can see that just like our simulation, they're right on top of each other, right? Everything is tracking very, very well. Okay. Now we're going to move on from here. We're going to move on to something that's a little bit, can be a little bit more confusing. This is going to be more of an advanced topic. So if you feel a little lost, no worries. Again, we've got, feel free to ask questions. Again, we've got great help topics to help you guys get through this. But just bear with me here for a little bit if you're a little bit lost, and I'm going to try to make this as understandable as possible. So let's say we've got multiple cylinders, right? You could say it's 2 cylinders, you could say it's 4 cylinders. Perhaps we want to maintain a level on all of those cylinders, but in addition to that, We also want to be able to control total force, right? So how do we do something like that? That's a challenge that's tough for a lot of controllers to achieve. We want to be able to move to a position or force and maintain that level. So I want the total force, right? If I've got a 4-corner press and one of the corners is sticking way up, either intentionally or unintentionally, I still want to maintain that level. I don't want to tweak my platen way out of shape and try to have the other cylinders press where they shouldn't be. I want the cylinder with nothing under it to be trying to maintain a level rather than just trying to exert a force on a part that isn't there. Okay, we also want to have the ability to level cylinders while we're stationary or we're in motion, right? If there is a different part of the system, not the RMC, that's controlling this platen coming down quickly, we want to be able to quickly, on the fly, be able to grab control of that cylinder and level it while it's moving so that, again, you don't have to increase your cycle time, you don't have a stop, everything looks nice and smooth, and you get your parts out faster. So what I'm going to do is talk about how we do this here at Delta and some of the theory, some of the thought process behind this. A huge thing to note, guys, we're going to be looking at gears here because it can make things a little easier to visualize. But these gears represent physical axes. So these are physical cylinders, right? Each of these physical cylinders, we're going to say, has 2 pressure transducers, one on either end, and a transducer that's giving feedback. So just keep that in mind. These gears represent those physical cylinders. Our first step in this process is going to be gearing a virtual axis to these cylinders. Now, what a virtual axis does is it's basically just a target, right? We've been seeing that light blue line, that target line that we had been gearing things to. Perhaps we don't really want to gear to another physical axis. Maybe we want to gear to just a pure target inside the RMC, right? Maybe we want everything linked up to one target axis. We'll call it the virtual axis. So our first step is we're going to be gearing our 4 physical axes positions geared to the virtual axis position. This transition, this clutching, right? How do these gears mesh? This is going to be specified by our transition in a user program. So we're going to make sure that everything comes together nice and smoothly and that you don't have any grinding of the gears. Okay, so once this gearing has taken place, this virtual axis, when you tell this virtual axis to move, you could send a move absolute command, right? Just like we've been using in this class, you could send a move absolute command. You could say virtual axis move absolute to a position of 5. As soon as this virtual axis starts to move, each of these 4 axes are going to move with it. So they're all going to be level. They're all going to be moving with that virtual axis, really similar to what we had just seen in that video where the 2 axes were moving in unison. It's going to do that, but we'll imagine that with 4 axes. Okay, now we're going to introduce another part to this system. I want to say this first. The goal of this approach is going to be getting a system that looks simple, is easy to program, and easy to work with. So what we're going to try to do is set up this whole system, which is fairly complicated, to look like basically just one big cylinder to your system, right? We want it to have a force and have a position, but we don't want to have to constantly try to worry about leveling things. We want the controller to take care of all of that and instead be able to focus on, I'd like to go to this tonnage or this position at this time, and make it nice and simple and not have to program and send commands to multiple axes. Instead, we only want to send commands to one axis to make it simple and easy to work with. So to do that, what I need to do is gear my virtual axis's velocity to my master axis output. Okay, at first that sounds a little confusing, and you wonder, well, why is that taking place? How does that make sense? Well, let's look at it back to the example of a physical cylinder and a valve. If I, and we were talking about the linear relationship, right? So if I output a voltage of 5%, I would expect, we're going to say it's a linear relationship, maybe I get 1 inch per second, right? If I output 10%, maybe I get 2 inches per second. If I output 5%, 10 inches per second, right? It's that linear relationship. You put output, you expect velocity. That's really what we're expecting from the output here. So we're setting up this relationship to look like that to the controller. So when this master outer loop outputs some voltage, it's going to translate to velocity for this virtual axis. So suddenly this whole setup, it just looks like one big moving cylinder to the master. So once this gearing has taken place, the master is in control of the system. We output some voltage. Those inner axes, these 4 physical cylinders, they're all going to move until you tell it to stop. But we've now got control with our master outer loop here. Now we say, well, we've got control, but we don't have any feedback yet. So we can't really do closed loop control. We can't work off our PID. What we're going to do is introduce some control. So we're going to say, what should the master's position be? What's that going to look like? Well, the position feedback to the master is going to be the average of our 4 physical inner loops. So the position coming from these 4 physical transducers is going to be averaged and sent to the master, and that then becomes our master setup. Okay, so we've got position feedback, right? We should be able to do position control here. The master you can tell the master, move to a position of 5. All the other axes are going to follow that master. It's going to get there very well. It's going to get there at the speed that you specified. Everything is looking good. But we still haven't answered, how are we going to do force control here? Well, we can give the master force feedback as well. So the force feedback is going to be similar but a little bit different. With the force control here, instead of just using the sum, or instead of using the average rather, we're going to be using the sum of forces, right? If you tell this platen, go to 10 tons, we want 10 tons total. We don't want 10 tons on one cylinder and 15 tons on another. We don't want this, odd force as it tries to maintain a level and go to a position. We want to make sure you do not go past 10 tons. That's the max that you're going to see. So therefore, the sum of these forces need to be trying to get to 10 tons if that's what you've told the controller to go to. So with this setup here, we have control over our system. The master is able to move, this gear is able to move, it moves this virtual axis, all of these inners all stay level, and we're able to control either force or position like this. Okay, here's just a brief recap. I know that this is a more complicated topic here, so I just want to go over it one last time. We've got 4 physical cylinders here. Each of these physical cylinders are being geared to a target, a virtual axis, target only. This makes sure that they're all level. Once they're set up here, we gear this entire system to a master outer loop. This master outer loop sees this entire inner system as one big cylinder, and it's able to control it. It's able to control the force, and it's able to control the position, and we're able to get accurate feedback from all of it and maintain level while we go through this. So with this setup, some of you may be asking, well, that's well and good, but how do we tune this? What is our tuning procedure going to look like? As far as tuning, you actually have to do less tuning than you would if you were to set up 4 physical cylinders for position and force control. The inner loops only need to be controlled or set up for position control, tuned for position control rather. So we tune the four physical cylinders for position control. These are all tuned, they're working great. It's really nice if you can do this while you're not connected to a platen so that they can move individually. You can get an idea for how the cylinders work, and you're able to move these really nicely and get kind of a basic tune on it. Then once you connect your platen up to things, maybe you do another fine tune and make sure that everything still looks good. It looks fine there. After that, what you'll need is your tuning for your outer loop. So the outer loop, once everything is geared and set up like we were showing previously, it is then going to be tuned for position control so that you've got still that nice, smooth, great position control. And then it's also going to be set up and tuned for force control so that you can do both with that outer loop. And again, everything maintains level, looks really good, and it's a really, really great way to control a system. Okay, so we've gone over the theory. What I'm going to show you now is how would we actually set something up like this in RMCTools? What's our first step, right? Step number one, set up a custom feedback program. This is going to be a program that is constantly running in the background. It's going to be sending over the position and the force feedback to that outer loop, right? This program, for the purposes of this program, instead of using 4 axes, we're just going to use 2. We're going to use that physical system that you've already seen. So as I'm going through this, imagine those 2 physical cylinders that we were just working with. Our purpose is going to be to synchronize these together and be able to press on an uneven surface, maintain that level, and go to a force. So just picture those 2 cylinders as we're talking about this. Axis 0, that's going to be the physical axis we've already seen. Axis 1, again, that's the other physical axis we've already seen. And axis 2 is that outer loop that we were talking about, that purple gear right here, this outer loop. Okay. So this is the new axis that has been introduced. I can see my axis 2 custom counts, and this is going to be for position feedback, is going to be the average of my actual position for axis 0 and axis 1. You can see that this program is very configurable. You can set these up for as many axes as you like. You could even do a different type of averaging if that's what you want. Many options with these, very user configurable. Now, we also need force feedback though, right? So our second custom counts, this is going to be our force feedback, is going to be our axis 0 actual force and our axis 1 actual force. So the sum of our forces together are then going to be giving us our total force. And then we also want to calculate our actual skew. We just want to see how well are these actually tracking together. Are they controlling well? Is there some issue? What does that look like? So my actual skew is just going to be the difference of these 2. Now, keep in mind, this is repeating every loop time. So if you have your loop time set up at 1 millisecond, every millisecond, this expression, as we call it, is going to be re-executed over and over and over and over again, constantly feeding new feedback. Okay, so what's our first step now, or our step after we've set up our feedback? So number 3, what you need to do, calculate the average position of the 2 inner loops. The reason we do this is just because, let's say one of our axes is at a position of 1 and another one's at 3. We want to calculate, well, what's the average? Average of those is 2, so we'll both go to the middle, get there at the same time. It's fine if they don't. It just may save you a little bit of time to calculate the average and go there. So we're going to the average position here, but it could be any position. We're then sending our reference 3. This is our virtual axis. This is our axis that is only a target. So again, axis 0, physical axis, axis 1, physical axis, axis 2, that purple, that outer gear, axis 3, that blue, that virtual target axis. Okay, in this step, we're going to wait until both axis 0 and axis 1 get to the position that they were intended to go to. We'll move on to our next step. Next, we're going to set the transition rate for these inner axes. This is our clutching, right? If for some reason things are out of whack, perhaps you're trying to transition on the fly and you can't just go to the average and wait there. Maybe you just need to specify, find the master and transition to it. We're going to be putting in this transition rate. This is basically a clutching speed. How do these gears lock into each other? We're going to say if you're out of position, you're going to be able to go at a maximum speed of 1 inch per second and an acceleration of 5 inches per second to get to where you need to be. So these gears then have this, these physical cylinders then know if I'm not in position, this is how I'm supposed to get to where I need to be. Okay. Next, we're going to use our gear absolute. So what we're doing here is we're gearing the inner axis position to the virtual axis position. I'm going to jump up really quick just to refresh what step we're on. We're on this step right here. This is what's happening. We're gearing our physical axes to our virtual axis. Okay, jump down real fast. So we gear to axis 3 target position. That's that virtual axis target. We're gearing to that target. Again, we're setting up a linear relationship. When the master is at 0, the slave, our 2 physical axes, are going to be at 0. When the master is at 10, our 2 physical axes are going to be at 10. And again, we just wait till both of these are geared together and ready to go before we move on to our next step. This is our last step. This is now connecting that purple gear, right? That last gear. I'm going to jump up again quickly. It's this master outer loop. It's connecting this together. This is completing our system. It's giving the master control over the system, and it's setting it up so that this this whole inner system just looks like one big cylinder. Okay. We use a gear velocity, clutch by time. We can set up a numerator and denominator. This just basically sets up the ratio correctly. If you'd like to look more into this, feel free, open up the help topic here, ask a question, but just know that this sets up a nice smooth relationship between the output of the controller and the velocity. Okay, master register is going to be our axis 2 control output. That's our master's control output, and we're going to clutch with a fairly short time. Okay. This is being sent to our virtual axis, and so after this is sent, we're ready to go. Things have been set up, and this entire, you know, it was fairly complex, but this entire complex setup has been built into 4 different steps. So you can see the thought process behind it is fairly complex, but that being said, we've made it so that it's not so bad to actually get things going. It's not going to take a massive amount of programming. It won't take pages and pages. It's just 4 steps here, and each of these are available from our website. So if maybe you're working on an application like this or will be soon, please reach out to us. We'd be more than happy to provide you with this example. Okay, what I want to show you now is RMCTools and how this is actually going to look in my program. Now I can see that I've got a custom feedback program set up here. So this this program here is constantly running my custom feedback. I can see by the little caret here that it's running right now, and constantly it's repeating, doing the same stuff that we saw in the slideshow. I've got a start gearing program as well here. This is, again, just doing what we were doing earlier. You can see I didn't even use the average here. I'm just using axis 2, and that's because it's kind of already set up as the average. But you can see that I've just got my gearing program here. It's not very long. It's fairly short, and it's not crazy to follow or anything. Okay, now let's see what does it look like if I want to send a sequence now to these commands. Well, what I'm going to do first is I'm going to run my start gearing program. I'm going to make sure that everything is geared together, everything's linked, and we're ready to go. Once that program has been run, I'm going to go ahead and do my quick move. Again, I'm trying to quickly move down, right, because I'm imagining my platen is up towards the top. I'm going to quickly move down here. Once I get close to my target, once I get close to what I'm actually pressing on, I'm going to slow way down. Once I see that 500 pounds, I'm going to then ramp up to 1,000 pounds here. Again, this is the same process that we just saw with the single cylinder, but I want to show you it with the 2 synchronized cylinders. We're going to wait till we get there, then we're going to delay for a few seconds, ramp back up to that 1,500 pounds. Once we get there, we again delay, and then we're going to be done with the cycle, right? We're going to get rid of all the force that we see, and then we're going to do a quick move back up to the top and be ready for our next cycle. So let me show you guys what this looks like here on a plot. Okay, I've got a few things going on with this plot. This is showing what my outer axes, my outer loop is targeting. It's also showing me where my inner axes are as well. So I'm going to run my program here. You can see my cylinders, they link together. I'm going quickly up, then I slow down until I see force. I get to my target force, do my slow intensification up to that 1,500 pounds. And now I back off from my force and I retract my cylinder. So you can see this is the same profile we've been looking at, right? I want to draw your attention to one thing right here, the actual skew. Let me get rid of these other items so we can just see, you know, how skewed are these axes? Are they actually maintaining a level? You could see this little purple line across my screen. I can see it jumps up a little bit. It looks like it goes up to about 3 thousandths at the max, and the entire time that we're in our pressing cycle, it's a lot less than that. It maybe goes up to 1 thousandths at the very maximum. So these are very tightly linked together. Okay, let me show you what that actually looks like on a physical system now. One second here. Okay, here is our physical system. So that's about as uneven as it gets. You can see we press down to that total force. Again, it looks exactly like that plot that we were seeing there. We're intensifying the force and yet still maintaining a great level here. Everything is looking really good. Get to the end of our cycle and we retract. I'm going to show you guys that one more time. Extend quickly, slow down right before, maintain our force, press a little bit harder. You can see the flexing on those rubber plates. And at the end of our cycle here, we're going to jump back and retract quickly. And there it is, right? We've maintained a level while going to a total force. Okay, I'm going to share my screen again here. So we've done it. I want to show you what those plots actually look like. So here's my plot here. And to be fair, I want to show you the actual skew on the real system as well. See this purple here? It's very, very small. I can see that it's jumping up and down a little bit as we're quickly moving. But really, it's going to about 2 thousandths. It is very, very level. While we're pressing, it's less than 1,000th of an inch. We're maintaining a level very, very well, and we ran through the cycle exactly how we were wanting to. So that's how we would do something like press leveling. I'm going to jump back to our slideshow here. What are some of the benefits to our approach for leveling? Well, first off, as we were hearing earlier, and now if you hadn't seen before, you've seen now, we have great position and velocity control. We're able to maintain really tight control over the system. We've got easy, smooth transitions from rapid advance to press mode. We've seen that whether it be single cylinder, 2-cylinder, 4-cylinder, however many cylinders you have, we're able to do a very, move as quickly as we can and then quickly decelerate so that we're able to make contact with that part very well. Something that's huge to Delta is that quick, seamless transition from position velocity control to force control, right? You saw with the linear, we overshot just a tiny bit. With our S-curve, we barely overshot at all. Again, it's up to you. Different applications call for different things, but we're able to do the force transition however you need it. Very good with synchronized position control while controlling that total force. Again, this is something that's a little more unique to Delta. We're able to control a lot of presses that other manufacturers aren't able to. Single axis to control once leveling is set up. So once this leveling is all set up, we're able to control by just sending those commands from a single axis. It's nothing too crazy. All we're doing is sending controls from that single axis. And I want to show you that, guys, just so we can recap. My dual force control here, it's only being sent to my outer loop, right? This is only being sent to my outer loop. It's the same sequence of events that we were sending out before to our other axes, but this is only going to the outer loop. So it's very simple once this setup has taken place to control your axis. Okay. So the next, what's next? What's the therefore here? Well, we've got many options, right? If you've got a maybe a single axis press that you're needing a controller for, the RMC75 is a great controller. It uses RMCTools. The programming is going to be basically the exact same as what you've seen from this class here. The RMC150 does great with a slightly higher axis count. Again, the same RMCTools. And the RMC200 is what I was using for the purposes of this demo. It's an awesome controller. There's a few more options with it. It's a bit quicker. Really great if you need if you need fast control, if you need to make sure that you've got some extra filtering options, or if you just have a slightly higher axis count. Really, really great option. As far as Delta resources go, I've been speaking about the Delta resources that we have, but in addition to what we've got on our website, we've got a very knowledgeable Delta sales team, a very technical team. Everyone is really willing to help you through whatever challenges you have with the RMC. Technical support team. I'm part of the technical support team. There's many other engineers who are part of the technical support team here. We want to make sure that you have what you need to get up and running. We've got 24-hour free emergency tech support. So if you're down and you need to be up, we want to make sure that we get you up as soon as possible. And we've got very knowledgeable distributors who are more than willing to help and have lots of resources to help you guys with whether it be the hydraulic setup, the RMC tool setup. We work with really, really great distributors. We've got application documents for your specific application, your specific press. Lots of 40 years of experience from Delta. We've done many presses and have lots of documentation if you'd like to look over and see if maybe something is ringing bells or you've got a specific application that's a little bit different from what you've done before. We'd love to speak with you about it. We've got application-specific examples as well. So whether it be a document or an RMCTools user program, we've got a lot of specific examples, step-by-step walkthroughs so that you can get to where you need to be. And we have these for whether it's a press you're working on or if you're trying to connect up and communicate with an Allen Bradley PLC or a Siemens PLC, whatever it is, we've got a document for you. Hydraulic design guide. I mentioned this a little bit in the beginning, but this is an awesome hydraulic design guide. If you're wondering, how should I design my press? Reach out to your distributor, reach out to us. We'd be happy to provide you with this hydraulic design guide. Many years of experience here at Delta has gone into this, and it's a really, really nice guide to have before you design something rather than after it's been designed. A few other things I wanted to mention. We've got a really nice advanced training course. What I did here was very quickly going through things. If you would like to come to Delta for a much more hands-on 3-day experience, highly would recommend signing up for our advanced training courses. You can look and see when those courses are available on our website under the training section, education and then training. And really, really nice. You'll get to actually physically use that 2-cylinder press that I was showing you guys in this video. You'll get to use that, you'll get to tune it up, and you'll get to do the leveling application. We've got many other hands-on stations as well, but it's a very good, intense 3-day course. So at this time, I want to open this up for question and answer. I know you guys have been asking questions in the chat box, and some of these questions have been prepared. I really want to thank you guys for being able to attend this class. And so without anything further, AJ, you want to take it away?
Thank you so much, David. As you mentioned, there are a couple of audience questions. Let's start with this one from Jerry. Using the RMCTools plots, could you possibly demonstrate a decompress from high pressure like that would be used in powdered metal pressing, for example?
Sure. Yeah. So let me open up RMCTools here. Okay. And so we're wanting to go up to high pressure, right? So let me set up one of these axes. I'm going to go into my plots. I'm going to start trending axis 1 here. And I'm going to use this right here to move right to where I'm going to see a little bit of force. So I'm going to do this quickly here. That's fine there. But what we're going to do is go up to force here. Then I'm going to enter pressure force control, and I'm going to do this with a time. For us, I think that the maximum I'm set up to go to a pressure or force with is fairly low. I want to say it's around 10,000 pounds, so I could ramp up to 8,000 pounds here. Maybe I'll use a S-curve linear. We'll do a ramp of maybe 5 seconds, and I'll send my command here. Let me change a few of my halts because right now I'm set up to kind of run these all together. So let me change a few of these. And give me a second here. Let's see. So we must have a shorter pressure or force set up here. What I'm going to do, let me just double check what my limits are. Okay, set up to a little bit lower. So yeah, this press can only, this example right now, we can only go up to about 2,000 pounds. So I'm going to ramp up to that. So now we're at 2,000 pounds, right? We could do a few things to disengage our force here, and it kind of depends, right? If you wanted to disengage very slowly or very quickly, we've got options for either. So perhaps I would like to ramp my pressure or force. Maybe I want to ramp back down. I'm going to say just ramp down to 50. Maybe you could say 0, but whatever you like. Maybe I want to do this in 0.1 seconds, right? Maybe I want to do this fairly quickly. Well, I can send this command here. I can see that I need a little bit of tuning still. That was a bit quick, but I'm able to ramp down and I'm able to disengage that force very, very quickly. Alternatively, if I wanted to disengage force and I wanted it to take a little bit longer, well, I could do something like that as well. Let me ramp back up to my 2,000 pounds here. Maybe I've got a process where I want to disengage force very slowly. I could ramp down to 50 and I could say, I want this to take 10 seconds or 100 seconds. It's whatever you want. So I'm sending this command here. I can see that I'm very slowly disengaging my force. And it's very smoothly gone down. This is a force of 50, but it's basically a force of 0. So there's a lot of options with disengaging the force. And really, you know, whether you're doing a powder metal press or any other type of press, we've got a lot of options for the force disengagement there.
Thank you. The second question comes from Perry. This is talking about the 4-cylinder gearing where you were discussing that example at the end. Could you show the axis definitions for this example?
Yes, for sure. Let me show you that. In fact, I'll set up access definitions for something like this. Well, it'll take a little bit of time. We could send over the example if you want to see all 4 axes. Right now, this is set up for 2. But if I were to set this up for 4, basically it would just be 2 more physical axes set up exactly like axis 0 and axis 1 are set up. So you can see on my screen right now, I've got position force control for axis 0 and axis 1. So just picture 2 more physical axes, axis 2 and axis 3, we can say, physically set up for that force control, for force position control. And then we've got an outer loop. This outer loop is also set up for position force control. And this is probably the axis that you want to see because this one looks a little different, right? So what we're going to be doing here is we've got our outer loop, axis type selected as outer loop. Our control loops are 2 loops, right? Dual loop, position and force. And then for our feedback, rather than choosing physical feedback, what we do is we choose a custom feedback. And we choose that for both our force and our position. And you can see my force is just set up as a single input because that program that we were using, let me set that back to custom, because that program that we were using, that program is then feeding into these custom inputs. So I've got this set up custom here. And then I just have a plain and simple virtual axis. So nothing special with this virtual axis. This is all that's set up here. But really where a lot of the setup takes place is my custom feedback, right? This is what is actually then feeding that setup for my axes. But it's nothing too crazy really for the axis setup.
Thank you, David. Last question comes from Norm. It says, when you define the outer loop from the example in RMCTools, is the selection for cascading outer loop?
Yes. Yep, exactly. Yep, great question. And yes, that is what you want to select, is that cascading outer loop.
Thank you so much, David. We want to thank all of you for joining us for this, for the very first Delta Computer Systems webinar. We hope that this has been informative and useful for you. To answer a common question in the questions, yes, we are recording this, and we will make this available later for offline viewing. And just to reiterate, if you do have questions, please, we are here to help and to answer questions. Please contact your Delta Regional Sales Manager. Also talk to a Delta authorized distributor. They can absolutely help you with your applications, can help answer questions. And then if you want to, we have resources available on our website. David mentioned the forums. David also mentioned our hydraulic design guide, which is available. You'll see at the bottom of the page, request a free design guide. We make that available to you to talk about how to design a hydraulic system for control. So thank you very much. We hope that this was informative for you. You will all receive a brief survey at the conclusion of the webinar. We would very much appreciate your feedback. And again, thank you very much for joining us. That concludes the webinar for today. And please watch our website. We'll get the recording available as soon as we possibly can. Thank you very much.